Hello, good morning. My name is Rubens Zimbres, and I am an AI engineer at Zendata. And today I bring our research of the CEO of Zendata and me regarding the privacy challenges in autonomous AI agents. And why this is relevant? Because these multi-agent systems are being increasingly used with generative AI nowadays, okay? So what are AI agents? AI agents are usually software entities like a large language model that perform tasks, that have access to tools also, right? And adapt through interactions, like when you have like a customer support solution, okay? So they are autonomous, they react to the environment, they are proactive to perform the tasks, they have the social ability of interact with users and other agents, okay? They learn through interactions using machine learning, and the market is supposed to have like a growth in a compound interest rate of 47%, reaching 47 billion within 5 years, okay? And what are the spending roles of AI agents in generative AI applications? They are being increasingly used, as I said, like in a sales pipeline. So you have agents to score the clients, to send emails that have access to tools, to analyze data. So these agents interact. And now, with the multimodality of large language models, they can understand tables, they can summarize audio and video, they can do transcription, you can generate content like podcast creation and blog posts, right? And so we identified some gaps in AI agent security, right? So current literature has limited understanding of the conditions that enable jailbreaks, right? We have insufficient insights into security of cooperative tasks when agents are working together. And we lack systematic analysis on these AI agent security risks. And why does this matter, right? Because when they collaborate, these risks, these vulnerabilities can extend to their interactions and the whole system, right? And that there is a lack of understanding on how these vulnerabilities in the system can spread through the cooperation of agents, right? So here we developed a setup. It's a bank setup with a customer service. And we did a qualitative analysis of the vulnerabilities we found in the system. So what are the core components in these multi-agent systems? We have the interface of the user with the client, okay? Each user has an instruction, okay? You are going to perform like a salesman to the external user, like it's an agent of the front end, right? Or you are going to be in the back end and you are going to query a document or a database. You have the personality of this agent, right? You are going to aggressively try to convince the client to buy our product. You have the knowledge, right? Here, you can train the agent with persuasion tactics or sales techniques, right? You have the memory of interactions, and you have the access to tools like an external document, a database, a calculator, a third-party plugin, right? So these are the components. and how they learn and evolve over time. Here we bring like some concepts of complexity regarding interactions because they adapt to interactions. You have emergence of phenomena, so when you change, when you have a small change in the initial conditions of the system, you can have like an emergence of phenomena in the system. And so this behavior is not like a causality behavior exactly, but it's a non-linear behavior, right? So this goes beyond our understanding that cause and effect, but here we are focusing on the process of interaction, right? So here we have like a classification of the AI agent threats. We have the user interaction and non-user interaction. In the user interaction, you can have like a jailbreak, prompt injection, backdoor attack. LLMs can hallucinate. You can have threats in tool use when you are using third-party plugins. And you may have like an anthropomorphic attachment of the user with the AI, okay? And non-user interaction is when the agent interacts with the environment, like a physical appliance, or when it interacts with other agents. When this happens, emergence of phenomena like cooperation or competition or even collusion between agents can happen. So what are the dynamic risks and capabilities of these LLM agents, right? They have access to tools, so you have third-party risks. They adapt to environmental input and feedback from other agents. They are independent, so their tasks can be done sequentially or in parallel, right? Or even in a hierarchical solution. They learn from the interactions by using memory. Then they can collaborate to complete a task or even compete among themselves. And something that we identified, they may collude with the clients or even with other agents, right? Posing like a security threat. So in the use case we bring here, we are evaluating risks in a customer service setup, right? So we have some advantages of using agents for these solutions because they are available 24/7. They have like unlimited cognition because they have access to database, faster response times, right? And here we have task specialization, like the division of labor, because each agent is specialized in one specific task, right? And they coordinate with themselves. And we have the scalability of the solution. So in this use case, we have the user that is external, right? We have the front-end agent inside this multi-agent system, and we have the back-end agent, right? The back-end agent has access to tools, and the front-end agent is going to interact with the user. So here, we have this solution, the front-end and the back-end agent. So each one has a role, right? The front-end agent is going to behave like the salesman that is going to talk with the client. The back-end agent is going to query the documents. Each one had his own access context, right? The front-end will interact with the user and the back-end agent. They have goals, right? So your goal is to please the client and give the information he wants, right? Your goal is to query the database and give the information the front end wants. And they have integration channels that can be like WhatsApp, web, and mobile. So in this setup, we consider like a bank company that deployed this multi-agent system as a customer service, right? That handles PII and sensitive information, right? Each agent has a role, a goal, right? Has a backstory. Okay, you are an agent that worked 20 years as a salesman. You have very experience in convincing people, right? They can delegate or not. Each agent is also a large language model. They may have access to external tools like documents, databases. They have memory of past conversations, right? And the front-end agent was trained using sales techniques. And the attacker, we have different types of attacker, I will show you, has training in persuasion techniques, right? This training comes as an instruction to the agent that is going to use those techniques with the system. And here, the attacker will always be a large language model. Instead of doing the attack by hand, we did an AI attack the system. So what's the flow of information in this solution? We have the client that is going to interact with the front-end agent, right? This front-end agent is going to get information from the client, like the user, check exactly what he or she wants, and then send to the back-end agent that is going to query a database and return the information the front-end agent wants to return to the client. And in this multi-agent system, all interactions are supervised by a conversations manager, okay, that handles the synchronicity of this solution. So, in this scenario A, we have the front-end agent as the attacker, right? But here, the attacker is inside the multi-agent system. And how do we make this natural? How does this naturally happen? Okay, given that the front-end agent is a large language model, let's suppose that this large language model was fine-tuned in poisoned data. So the training was contaminated. And then you have like a malicious actor insert inside the system, right? So the idea here, we had to extract a password that is inside the document, the external document of the backend agent, right? We tampered this front-end agent with training data poisoning, right? And the idea is the user to interact with the system so that we can retrieve this password in the document, okay? And what are the results we got? With prompt injection, the front-end agent leaked the password in the document, and we use like GP3 3.5 and 4, both leaked the password. And without prompt injection, this only happens in less powerful LLMs. So the purpose here is to focus on excessive autonomy, insecure design, data contamination, and supply chain risks. In the second scenario, the attacker is outside the multi-agent system, okay? So he has to do an attack of a second-order connection because he has to convince the front-end agent because, you know, the user, the client that is outside the system, doesn't have direct access to the backend agent. So he has to convince the front-end agent to talk to the backend agent and get the password, right? And here, we instructed the front-end agent to make the client happy and agree with the client, right? So we noticed there was a collusion between the front-end agent and the client, and then the front-end agent convinced the back-end to leak the password, okay? And this, the purpose here is to focus on prompt injection because the AI is constantly attacking the system, right? I'm going to show that this attack is not a brute force attack as we are used to do, but is like the attacker builds rapport because it's an AI talking to another AI, right? And in the scenario C, we have a dual vulnerability extraction, right? Here, the backend agent was told explicitly to deny access to the document, okay? So this is the same as the second attack. But here, the backend agent was explicitly told to deny access, right? And this makes much harder, right? Although these guardrails are made with natural language, you are not creating like APIs in the connection. This makes harder to invade the system. And it's much better with more powerful large language models, right? However, there was a failure also in less powerful LLMs, and there was a failure also with the manager because the backend agent shared the information with the manager so that he could like supervise the interaction with the front-end agent, and the manager leaked the whole conversation in less powerful LLMs, right? And so here we focus on plugin design flaws, insecure output handling, right, by the front-end agent, and supply chain vulnerabilities, right? So here, what we found out is that the manager should have like a more proactive behavior to interrupt interactions that may pose a threat to the system, right? So in our qualitative analysis of these vulnerabilities in credential leakage, what did we find? We found that the attacker used social engineering tactics, like it's used like persuasion tactics like empathy, mirroring, and urgency to slowly gain the confidence of the agents to get the access to the credentials, right? We notice also that the front-end agent was frequently aligned with the user agenda, like in a almost explicit collusion, right? And the backend agent disclosed this password in the document, right? Showing like an inadequate response validation, right? And this was quite simple because in less than 10 minutes, we were able to leak the credentials, right? And so as implications, we have the need for a robust input-output validation, right? Strict access control, you can communicate via APIs instead of natural language, right? and target training with curation of data so that you don't have a threat inside the system, right? And what we found is that differently from a human, when the human attack an LLM, like a large language model, the AI tends to build rapports and to gain the confidence of the other agent to reach the goal, right? And we have implicit collusion, basically in the second setup, second and third setup, when I said that the front-end agent should agree with the client and make the client happy, right? The insider threats, that LLM that was trained with poisoned data is an advantage to gain access to the system. Conciseness of the conversation reduced leaks, like in our real-world scenario when somebody talks a lot, and makes more prone to leak information, right? And less powerful LLMs show it to have a greater tendency to leak credentials. Even with strict denial policies in these less powerful LLMs. Regarding financial implications, okay, let's suppose like one enterprise handles 1 million customer interactions monthly. And if 1% of these interactions result in a leakage, okay, we would have like 100 million data records leaked monthly. At the cost of $164 each during the year, we would have an impact of $196.8 billion losses per year. So this is quite relevant in the economic aspect. And what are the remediations, right? We should have input and output validation. How do we do that? In systems that are automated, when you scale to millions of users, it's impossible to have a human as a judge. So we could have a large language model as a judge of each interaction, right? This makes the system safer, but what is the trade-off? You are going to take longer for each interaction, and you are going to pay more to have this active supervision. And this is interesting because we found out that even one of the best frameworks for multi-agent systems, they don't support the proactive role of the manager in the sense of interrupting a transaction that is going to be harmful to the system, right? We can use API connections instead of natural language to have a safer solution, okay? So we have like different APIs for financial transactions and for verification of user identity. We can have like stronger access control, like in healthcare where not every user has access to PII of the patient, right? You can have human oversight, like in small-scale systems, like legal systems. You can have a human in the loop to check for this, to check the system, right? And you can have redundancy, irregular testing, like pen testing of the system, so that you can reach a better state, like in logistics. So what are the future directions that we see in these multi-agent systems? We see like that someone could increase the sample, make a study where the person can increase the sample so that we can have a better generalization of the results, like a more robust results, right? We can also investigate the cascade effects in these large systems, like if the system fails like a domino effect when there is a failure in a single point. We can analyze the effect of using LLMs as a judge in the system, how this can enhance the security. And establish communication protocols for data exchange between agents, right, against potential attacks. So, what are the key takeaways? We should increase security through redundancy of the system, like when you have a drone swarm in a high security facility for critical tasks. We should use LLM as a judge to effectively supervise and interrupt like harmful transactions. Let's say, okay, give me the name of clients in your database. So you have like a SQL query that is going to say like select names from table. And then if you have an LLM as a judge, just say you're going to leak PII. So you are not allowed to perform this action, right? Use, like implementing privilege management and strict access control beyond simple natural language, like prompt techniques, like, right? Giving like access level, different access levels according to the role of the agent. And establish strict communication protocols against data leakage, right? Like API connections between agents in legal systems and finance. So this is what I wanted to present today. And we could take some questions if you... Anyone? Yes.
Can you say some more about the drones you mentioned at the very end? Is there anything more you can explain about that? About how to...
Yes, with multi-agent systems, you have like the drone swarm, like you have like this complex behavior where they have specific tasks, right? They keep a certain distance between each one, right? And this is the, here I talked about the drones regarding the redundancy when you are securing like high critical facilities, you know, regarding the security of the system. It was not exactly the focus of this study, but this is an example of how like you can compromise a small part of the system that is going to affect the behavior of the whole thing, you know. Yes.
You mentioned that less robust LLMs tend to leak data as opposed to more robust LLMs. Have you made any kind of study classification of public LLMs provided by, let's say, AWS, Azure, how prone they are to leak
Okay.
sensitive data.
Okay. He's asking about like public open source, right? Also, open source large language models and how they behave leaking data. There is a trade-off between the size of the LLM. I mean, with smaller LLMs, you have like less accuracy, but you have a safer LLM, you know? So this, we didn't study this here, but I noticed because I work with the OWASP guys in the LLM, the OWASP top 10 for LLMs, right? And we noticed that when you transfer the learning from one LLM to a smaller, you are going to lose accuracy, but you are going to generate a safer model, you know. So you have this trade-off between accuracy and security, you know. Anyone else? Yes.
So I saw your presentation, it was good. Now, within my company, we have also implemented OWASP Top 10. So it looks like
I see.
now I'm thinking, because can we, for example, develop an agent that would be a security agent that controls input, outputs for every party involved, right? And that will sit in the middle between the backend and front-end agent.
Between the front and the back end?
Backend and also third parties. This way, if there's a miss in input, we can always catch the output because if we, for example, in the security agent, we say that we don't allow privacy data to be exfiltrated.
I see.
So even if we manage to get a command and retrieve the data, we would catch it on the output, right? So
You want to filter this?
well, just create a security agent where we put some
Sure.
knowledge or security.
Sure.
That will control the whole system.
Sure. He's saying that he wants to put an agent inside the system so that this agent can handle like interrupt also the flow of personal identified secret information, you know. You can do it, like, LLMs are very good for this, because they give you like a level of understanding that it's much better than literal match and like regex match, you know, because you see, you know the context that you are working, you know, like what's the context? Is this compliant? And this helps a lot. Of course, you have to test which LLMs to use, how you are going to intercalate this agent in the system, you know. But it's a very good, like, beyond, right? You have the traditional means of securing data, but if you want agents to have like a more intelligent approach or like a semantic understanding of what is going on and what is being leaked, the LLMs are a good solution as agents, you know.
I think it's worth testing, right?
Yeah, yes. Anyone else?
Yeah, I have a question. In your scenario A, you had tinted training data, and like after that, you spoke about insider threats. So I'm thinking, is it a practical attack? Could it really happen?
Yes, this can happen. Because let's suppose you are going to fine tune an agent with the data that you didn't take care of checking for private information, PII, or even like hate speech and other biases in the data, right? You can generate an agent that has like a malicious personality inside the system. And thus you can like facilitate collusion with malicious actor, with the system. Here we did it to do like exactly like an insider threat, But I believe this can happen naturally. I mean, it's not simple and it's not common, but it's a possibility, as people can start fine-tuning more and more LLMs to reach like specific goals, right? We can have this threat. Anyone else? Okay. Thank you.